It's my pleasure to introduce Dr. Min-Yeong Moon. Min-Yeong is the lead algorithm engineer at the Advanced Algorithm Group at KLA Corporation. Our group develops advanced machine learning, deep learning algorithms to solve challenges in metrology. She obtained her PhD in mechanical engineering at the University of Iowa in 2017. And after that, she was a postdoctoral research scholar focusing on confidence-based reliability design, optimization, reliability assessment, and uncertainty quantification, given the lack of testing data. Her primary focus currently broadly includes machine learning, deep learning, and probabilistic modeling, especially robustness improvement given the lack of limited real-world data and uncertainty quantification of machine learning models. And we're very excited to hear her talk.
Tom, thank you for introducing me. It's my pleasure to be here to present what our group is working on. Today, I'm going to present what are the challenges in the metrology, especially machine learning point of view in the semiconductor device industry. I brought two main kinds of achievement. Just want to ask you which one seems more complex. The first one is NASA-75 rocket, which has 3 million of parts. The second is 800 graphics engine designed for AI and blockchain applications, which have more than 50 million of transistors. Maybe hard to say, but also I'm not going to pick one. And just wanted to say that one of these is the one I'm going to talk about the rest of the talk. I also want to note that if you want, you can only manage, control, improve only one. There are things that you can measure. So what's the matter of measuring? I would say it's very fundamental things of all the engineering, the technical field. If you think about your daily life, it's plenty of things involved in the measuring thing. You go to gas station, you fill up gas, you need to know how much it filled up. That's also measuring. Furthermore, whenever you measure anything, there has to be the system behind to confirm what that means. So I would call that metrology, which is science of the measurement. It's used for data analysis, so process monitoring, process control. It's been really widely used for the many industry. For example, if you imagine the automotive industry, might be curious how come they are able to manufacture all these identical parts, bunch of identical parts. I would say that's beauty of the metrology. But today I'm going to focus on the metrology in the semiconductor device manufacturing. I also want to give you a little bit of the background. This is the wafer. It's a thin sliced silicon, on which electronic circuits fabricated. And it serves as substrate. And inside, there's a tiny pieces of silicon. It's called chips. And there is also, you see this line, it's called the scribe line, which is non-functional line, where so can cut the wafer without damaging the circuit. And inside the chip, there are a bunch of the transistors. I would say it's millions of the transistors there. So basically, we want to measure this shape of the transistor. Next, I want to introduce the concept of the transistor node. You may have heard of this, some of the article. It implies physical size of the transistor. It's a single metric that's characterized different transistor technology generation, roughly predicting the performance of the transistor. So basically, the smallest feature that can be manufactured. This left plot shows that as the transistor size is scaling down from 130 nanometer to 2 nanometer, and you see the number of process steps required is pretty much increasing. Intuitively, you can think of that making smaller transistors require more complex process. it's hard to manufacture, also requires more precise manufacturing. So that's why it's increasing. And here I'm showing the three types of different transistor. First is called the planar FET. It's a 2D design transistor where the channel lies on the substrate. It's flat and substrate. But the problem is when this size is scaling down, there was performance limitation due to the leakage current. So next generation, it's called FinFET. It's a three-dimensional transistor. You see this channel is shaped. It looks like a pin, and it's surrounded by it's a three sides here, and it's improving the performance. And you can make even more smaller size better. This is another generation. It's another types of three-dimensional transistor. Now the channel is completely surrounded by a channel on the four sides, and this channel is look like a strip. It's going through the gate, and that's why it's called sometimes nanosheet. We call this state all around. Typical node size is 5 nanometer, 3 nanometer, and 2 nanometer. And still, I mean, this semiconductor industry is continuously developing this transistor, and I would say beyond 1 nanometer size, it's a research area. So what we are measuring is basically we are interested in the shape of the transistor. We measure the CD, top CD, bottom CD, the height, and the sidewall angle. So these are the things that we are measuring. And also interesting to achieve the device performance. Just for the better understanding, I brought some cross-section image of the transistor. Top one here, it's FinFET from the Intel 22 nanometer to all the way up to 10 nanometer. And you can see here, this is the fin. Basically, the shape of this fin is the key of this following the metrology. The bottom is a nanosheet image from IBM 2 nanometer. You see here that the 3 nanosheets. And this right side cartoon is showing that what kind of parameter that we are measuring.
So quick question. For this nanosheet, is this a cross section?
Yeah, it's a cross-section image. Yeah.
I'm sorry, what did you know the spacing period on that?
In this specifically, sorry, I forgot the number.
It looks like a few nanometers from that.
Yeah, nanometer. 5. Sorry, I forgot everything. And how do we measure this one? I'm trying to focus on using the machine learning approach. So we use machine learning model that's input. We take the optical signal as an input. Our company has another X-ray tool that we can get an image as an input. So those are the input from the optical signal or the image from the sampling tool, X-ray tool. And we train the machine learning model to predict the critical dimension that I show, like height, the CD, or all this. And just to show how we get this optical signal using the simple ellipsometric principle. Here, the light source is coming as an unpolarized wave, and this polarizer is making the light is linearly polarized. Basically, it's reflecting on this the wafer, the sample here. So depending on the layer structure, this the linearly polarized light is kind of differently distorted, and this compensator making this linearly polarized light the elliptical polarized light. So basically, by measuring the change in the polarized light, we can, depending on different layer structure, we can identify the unique optical signal. The different structure will have the different distortion, and we can measure the unique optical signal. Yeah. Also, I want to introduce what are the evaluation criteria that we are interested in. The first is called, there are several metrics. First one is called the precision. That's, in other words, the repeatability. So basically, we measure the same wafer and same site, let's say 10 times. And ideally, the measurement, the prediction, machine learning from the prediction, 10 times should be identical. But the short noise is slightly different. And we're trying to minimize those variance of the prediction. That's called the precision. The other one is accuracy. We have the other reference tool like image space. We can get the reference parameters, the reference value from the other external Metrology tool, but that's usually destructive, unlike the machine learning. So we typically compare bias to the reference between the machine learning prediction value and the reference, also the correlation between the reference. Definitely, we want to make sure that high accuracy. The third thing is it's called the tool matching. Typically, we in the same wafer, same site, but we measure from using the different tool. Basically, imagine that measuring this using different ruler each time. And we want to make sure that all the measurement from different tool ideally should be identical, but there's two uncertainty, tool shift, it's not identical, or we want to make sure that minimizing those variability. The other terms I wanted to introduce, it's called the sensitivity. In general, it means the comparable between change in the output and change in the input. So in our case, you can think of how much the signal is changed with respect to this parameter change. So imagine the low sensitivity case. So low sensitivity case means think of this 2D feature space, signal space. Parameter sensitivity is very, very small. What that means is the output is dominated by the signal noise. So we can tell it's due to the signal noise. Let's say signal change will perturb some parameter, but we don't know if that's due to the parameter change and signal noise because the sensitivity is too low. So in this case, it's very challenging for the measurement metrology. But if it's high sensitivity, we have a pretty good sensitivity enough. So even though we have some signal noise, the signal change is pretty large. So it's pretty much easier for the machine learning to predict for better measurement capability. So this is also one of the challenges for the low sensitivity parameter. How can we tackle this? And for the machine learning in the metrology, in our company, KLA, we have the ML in-house product called TurboShape, which our team is developing the whole algorithm. You may think of why machine learning is needed. As I mentioned, the external tool is destructive, meaning that you have to destroy the wafer. So it's not good. And also, you can use some physics-based solver, but that's usually supporting the local minima. What I'm saying, local minima is depending on where you start your optimization, it may stop into the local optimal point every time different, but also long time series. But machine learning can enable automatic metrology system to monitor the wafer inline. So we can make better productivity with the better cost. And these are the key objectives that we are aiming. First, I told all these precision, tool matching, those metrics, we typically need to minimize called total measurement uncertainty. It's minimizing precision, tool matching, the accuracy, the reference. I want to talk through objective a little more detail. You may be aware that machine learning, let's say, for those we are trained on, the space that we are trained on, machine learning can be pretty much predicting accurately. But once it's going outside, you get a new data, and that's I haven't seen before. It's not a training data. It's basing, it's basing difficult. So I call this is robustness. It's basically the ability of the well-trained model to predict unseen data with the good accuracy. So this is really important for us because we are, once we develop this machine learning model, after the verification with some holdout data, we deploy this recipe on tool. We monitor the wafer, let's say a few months, a few weeks. But if this breaks, machine learning recipe breaks, then it's problem. So basically, this robustness is really important, especially in high volume manufacturing environment. There's another challenge is coming. It's called process variation. These are the illustration of the different types of the process chains. First case, you can think of here, I'm just illustrating the different wafer over the time. You can think of everything looks okay, but just few of the wafer could be the outlier, flier, and we want to patch this. The second case is process chains. It's stepwise, just a sudden process change. The other one is gradual process change. So all these process changes happening, which makes the machine learning recipe to be not robust somehow. So here I also brought the illustration of the process shift in the signal feature space. Although the signal is really high dimensional, imagine this three-dimensional signal space. And here the blue color one is, let's say, production wafer group 1. And over the time, and you can see the signal is gradually changing. It's basically the process changing happening in this direction. Let's say my machine learning model trained on this production wafer. And later over time, after 1 month, we got a new wafer for this red one. And if your model is not well generalized trained, then you're gonna be in trouble. Yeah. So we really need out of distribution generalization for the machine learning model. The other objective is I mentioned that we are monitoring the runtime, the wafer. Basically, what people do is brute force periodic retraining. Basically, every weeks or every 2 weeks or months, we add a new wafer to retrain the machine learning model. So make sure that the model doesn't break. So what's the problem of this? Let's say if the frequency of the changing, the refreshing is faster than or process or slower than process change, then we are going to waste of the money because you have to get the reference. I suppose that's the disruptive. That's one. Also, if the process change is lower than the frequency of the retraining, then we may miss some of the out of distribution wafer. So it's not good way actually. Without knowing anything, we just brute force the retraining. That's not good. So I would say this is really a challenging problem. We need a really accurate quality metric, which is quantitative value for the measurement concern. It's predicted by the ML recipe. So what do we want to answer with this quality metrics? When does this recipe break? And when to retrain? Also, how to detect the problem wafer? And let's say we decide to retraining, but how many wafers we are going to add, which wafer we are going to add. That's all kinds of decisions that we have to make.
So I have a quick question. What are you predicting? Because I think you said you're predicting the critical dimension, but I don't know what that is. Is it critical dimension like the length or?
Yes, the height of the 3D,
Okay.
the structure, the layer. Yeah. Also, we also sometimes predict overlay, which is a misalignment between the multiple layers. There are a bunch of parameters we are predicting. Yes. That's what I meant critical dimension, which is output of the machine learning. And we are monitoring here those parameters. And on top of the measurement, I'm saying here we need some kind of metrics to say whether our prediction is good, when to retrain my recipe, things like that. Yeah. So, so our team is actually tackle this challenging, all this challenging. Basically, these are the main challenging. Robustness challenging. I mentioned what is robustness, but the more challenging is we are facing the lack of data. So the getting the real data is very limited with the ground truth reference. Also, we have the mixture of data, reference data, unreferenced data. Unreferenced data means we don't have the ground truth value, but we have only the signal of the signal. The reference data means we have the both signal and the corresponding the reference parameters from these other tools, the reference tool. Second challenging is how to access this quality metric accurately and unseen data. I mean, training data definitely we can assess the quality of the measurement, but how do we assess that the unseen data? And the time to solution is challenging because the process is evolving and we have to predict the parameters, the different process step and different node, the layer. So many, time to solution is also challenging. Also in the same device structure, we have plenty of output. The parameter needs to be predicted, typically 10 to, can be up to 23 parameters. So, but I want to focus on these two, not these two. First, two bullets I want to focus. Yeah, first one is robustness challenging given the lack of data. I mean, there could be many solutions to tackle this, but I just wanted to show one way that we prove the successfully. One thing is to use synthetic samples to aid the real data performance. Our product is basically the model assist output, which use synthetic data and the real data to be trained together. So basically, these parameterized structures using the ISW, we can get the bunch of the synthetic spectra as well. And meantime, we collect the signal from the real wafers, and these are the real spectra, and we use them together. Usually, it's unbalanced. These synthetic spectra is a lot, say 10K, 20K, but the real data is much less. And we train them together, build the machine learning model. Our team, the machine learning, we have our unique framework that can automatically select the best model. And we confirm that's okay on the test data, and we deploy our recipe. So that's the typical recipe development procedure using the synthetic data. Here's some success use cases. This is the overlay measurement on DRAM. I'm comparing the three outputs. The left one is machine learning, but modelless, meaning that we only use the real signal. Middle one is reference. It's a destructive reference tool. The last one is our product, which is modelless. This box plot showing the wafer within wafer range. Each box you can think of different wafer. this bucket is a different lab. So basically, we want to make sure that this mean trends from the reference tool, same as the prediction from the ML, also the reading wafer range. You can see from the model list, the mean is really fluctuating a lot compared to the reference. Also, the reading wafer range is pretty much overestimated. However, if you look at the model-based approach, mean trend is much more resembling to the reference. Also, the reading wafer range is also very similar. So we confirm, we have many more use cases, and we confirm this model-less machine learning is really struggling replicate wafer-to-wafer mean trend, also the reading wafer range.
Does the model in model assisted refer to the? It doesn't refer to the machine learning model.
It is a machine learning model both. These are machine learning model both.
Right. So what is the model mean? Is that a physical model?
Yeah, this physical synthetic.
Oh, okay.
So basically, model list means we only use this part. We collect the signal from the real wafer and collect the reference from the tool. That's the only data we are going to put it in the ML. But whereas model based, we construct this parameterized structure. Fairly good accuracy. It's not 100% accurate, but it's fairly approximated. So we can generate a bunch of the synthetic spectra. Even we can calculate the parameter space. Like you can generate hypercube, hypersphere, different sampling. So we typically calculate those samples in the high dimensional parameter space and generate the synthetic spectrum.
Okay, so the model based is just it has like synthetic data augmentation.
Yes, on top of this small size of the data.
Okay.
And basically, the fundamental behind why we see better performance is basically we can generate the synthetic spectra to cover the large process variation, although that's not 100%, but that makes more robust solution. The second challenge that I was mentioning is how to ensure the quality of the measurement from the machine for the runtime. In this our application, there are even more factors that makes more challenging. The first one is what I call the reference tool to get the reference. It's not 100% accurate. There could be some factors there. So that actually contributes the performance of the uncertainty quantification as well. And we really need quantitative metrics, not only account for this out of discrete domain. If you look at a lot of research paper, there are a bunch of papers talking about how to detect out of distribution domain. But what we are also interested in is, let's say this purple is training domain, and these gray is out of distribution domain. We can detect out of district domain using whatever state of art research idea, but there could be the yellow area that still the machine learning model is robust, even though the domain is out there. We want to catch that. This is the challenge. Basically, we want to catch this area, not this area. Also, the quality metric should not be sensitive to the signal noise. We have some signal noise level. This should not be catched that. Also, different parameters may have different uncertainty. Even in the same step for measurement, same machine learning recipe, different parameters have different uncertainty. And the more important thing is we go customer to use this quality metric. We have to provide some kind of threshold. Okay, after this threshold, this recipe needs to be retrained. But the selecting threshold is also a challenging problem because we have a different node layer application and how to set up the threshold. Basically, the confusion matrix, the one of the metric that we are looking at it to check the performance. But this false positive, false negative, it really depends on how we set up this threshold. For example, here I do a very simple illustration. X-axis is the machine learning error, y-axis is our quality metric. But if we set the threshold a little bit lower, then you see that there's both positive here, both negative here. But when we increase the threshold, you see the first positive rate is better, but the first negative is going up. So it depends. It's the same. I'm using the same complementary algorithm, I'm doing the same machine learning recipe, but just depending on how I set up the threshold, first positive rate, first negative rate would be varying. So then how to measure this quality of the measurement? It's very related to the uncertainty quantification. I'm not sure whether you are familiar with this concept. It's really core of the understanding of the ML model reliability and robustness. And there are two types of the uncertainty. The one is aleatory uncertainty, which is inherent randomness, something that we cannot reduce. I think about you are predicting the light durability of the wind turbine, but wind speed is something you cannot control. Its speed is always varying, and their randomness is already there. So it's not something we can control, but usually it's parameterized by probability density function. And the other type of uncertainty is epistemic uncertainty. It's something we can reducible. So it's mostly related to robustness in the real world. I break down these epistemic uncertainty to different parts. The first one is data uncertainty. It can be related to some data corruption, labeling, missing labeling, and maybe we may not have some enough training space or sample size. Another one is a procedure variability. Something noise from the training procedure. We are using machine learning, could be random initialization, all these things. You can think of some variability. Another one is model uncertainty. This is, I think, a big part of the from the epistemic, which is really fundamentally the model that we are creating. So we don't know this can really explain the new data due to the discrepancy between our best model versus the real one. And approximation uncertainty is something, say, some non-optimal model within our test of the model. So for example, here, let's say this is my domain. This part is model. Say at our two real world. This model uncertainty, even though we can make best model in our domain, there is discrepancy between the real world. And this is the approximation uncertainty, whether we didn't make good job or we didn't optimize our model. All these kinds of uncertainty. But these are uncertainties we can somehow control. So we can estimate somehow. So what are the questions that we want to answer through this uncertainty quantification is it's more easy for the classification problem. You just detect out of distribution, misclassification, defection. But in the metrology problem, which is more like the regression because we are predicting the CV. So it's a regression problem. We want to answer when does model being stock reliable, incorrect measurement, outlier site, and how to judge the quantitatively. And we want to guide this uncertainty quantification using this to guide to how to improve the model. So there are a bunch of the papers talking about the uncertainty quantification, including Bayesian, Markov chain Monte Carlo, and Struggle, various methods, Gaussian process, ensemble model, probability, so all these things that you can use to quantify the uncertainty. Also, the question that you can think of is for the uncertainty quantification, it's something on top of the measurement. Are you going to use some kind of meta model or more complicated model? I can also think of that as questions. Next, I want to show uncertainty quantification use cases in our problem. This first piece is detecting the incorrect measurement size. So this plot showing the uncertainty wafer map. Blue one is the you can think of the lower uncertainty size. Red one is high uncertainty size. So the left case is the wafer with all the correct measurement. But the right one is the wafer with including some incorrect measurement. And we are able to find this incorrect measurement by looking at the high uncertainty size. High uncertainty size. And the second one is I've told that there is some process change over the time. Think of this x-axis is the wafer. And these are the wafer before the process change. And the last wafer are the wafer after process change. So by looking at the quality metric, the monitoring, and you can see that the uncertainty is growing after process change. But there's some delay, we call this lag. And another purpose, goal is that we want to minimize this lag. I mean, we're not able to detect it right after the process change. And maybe we can detect, can wafer, so that's lag.
And so what is blue and what is orange?
Just two different approaches. Uncertainty quantification.
Okay.
Yeah.
Okay.
I go for two different approaches. Another use case is it can be used the one-time monitoring. They we deploy the recipe on full automatic measurement, monitoring measurement as well as this quality metric value at each site for all the incoming wafers. So these are the all unseen data for this recipe. And we look at the trigger condition, which site or which wafer is over them at some kind of level. If it's yes, then we do some fine tuning and retest the recipe and keep monitoring. If not, then just we keep doing the monitoring process. So to improve this model reliability, usually the fine tuning the ML recipe by adding some proper wafer where the quality metric is high or worse. So you can see I explained we can propose periodically training, but if we do use this trigger, we can save a lot of wafer because this frequency is too frequent. It's faster than process change. Basically, if we trigger the recipe by this quality metric, we can save time, also the cost. These are the summary of this talk. I introduced the importance of the metrology, what kind of metric that we are interested in, also what are the objectives of machine learning in the metrology, and also what are the challenges that we are facing. And especially I was focusing on the robustness, given the lack of data, and how to quantify the uncertainty, to measure the to predict the quality of the error prediction for the monitoring. Yeah, that's all for this talk.
Question about us using if you did into this thing, and I don't know if this picture you showed on the last slide, and you did a little bit, but we have to do several, like what's the cost of doing just one wafer? Is it sort of such a, big process that in there is often on many wafers at once, or is it reachable to just, say one wafer at a time, and that's possible to do as well? So you're saying what's the typical way of producing, but it's like one wafer or a bunch of those. I showed you graph there that so if let's assume that's not outlier, we consistently measure the typical cross-section is gradual, it's consistent. So there are many ways, but there are lots. But if you like, we have multi-wafers. These are the high energy. So we typically and do all flash. It may not be usually it's not a single wafer. If you find a single wafer, that's also flier. So if when something happens, the process will happen. It's more like a good lab. Yeah. So in our team, it's also so we are trying to figure out what's the best approach to the fine tuning the machine learning. I mean, we don't want to do the training from the scratch. That's taking a long time. And what can we use for the fine tuning of this? Because otherwise we want to have reason. So that's also we are something investigating for what we want to do for the time solution. The question I have, so when these process changes happen, and let's say you need test or anything on the whole lot at some time, is there a point at which you feel you need to throw away like very old data that you say the process is so significantly different now than the way it was when you first trained the model, for example, even the just throw away biotech. We communicate with customers. So basically, okay, these are the labs we found in Thailand, but we do not have any spots. So they are the experts of domain knowledge. Maybe they might be trying to do presentation really good process like then we may show the old one, but otherwise I would say we don't show it. I'm speaking with those data to it actually makes the latest state to be better. So it's good to add all the data is available. So I show you that using the very data copy. But one of the reasons is definitely we can improve the project space, not a 15 minutes when we create the feature space where we can better representation. So that's exactly. Thank you.
Yeah, because what needs to be accomplished and we have also got
So
yeah, the process changes. So what is the cost of that?
what is cost? That is something, money. And I have more, actually, you're asking what makes
I'm just trying to find it. It's possible that some people will tell you the information, but the market may change. And if you have another information, yeah, the total backwards, it's possible to get out the final
So
information.
it's something that was intended by the customer, that we know what sometimes the processing it may not be intended by the customer. So that's something we want to identify by the customer.
So I'm going to preface that all of my knowledge in this space is physics based, and I know almost nothing about machine learning. So this is an ignorant question. But in fitting physical models to measure data like this, I know how to quantify uncertainties and put bounds on the parameters I'm extracting, and also to try to determine when I'm overfitting a problem. And I know all of that's a danger in this space. In the machine learning world, can you quantify that? We're estimating the bottom CD with this uncertainty, or perhaps the user might be asking for data that's just overfitting the particular.
I see the two questions here. Where the first one is whether the machine learning can provide some kind of bond, right? Yes, I mean there many probabilities, of course, everything is out distributed. The macro thing output, we think the machine learning is like MPOs, we can get to something output, but there is a probability where we can get that out of distribution. And the thing output at each measurement, and we can do sort of the bound with some kind of contact level.
That's very useful information. That's all related. The question that we have is, how do we know whether the machine learning is overfitting? That's the question. That's actually really also something that we are working on, because you know, if we use very complex machine learning with many number of different complex big data. But if that's still complex, then the problem area is already involved. So we are really good at predicting what the first can data, but not good on the first data. So there are many ways to avoid overfitting. I haven't talked about this. That's more like machine learning. We can do the first validation, we do some regularization functions, individual functions, all of that. All those, we are using all those kind of techniques to avoid the fitting problem. Make sure the single, it's really hard to identify what certain architecture will be facing problem. And certain problem, the layers could be very simple, very complicated. The number of samples we will get might be fictional. It's really depends on the partner, and we have to identify what architecture for each problem and those challenges that you mentioned. Any more questions?
I guess I have one question. So, in your setting, you have this large wafer, and the wafer is covered in transistors, and you want to measure each transistor, right? So, are you trying to measure them all at once, or are you like measuring individual one?
We not whole thing. Basically, we measure each step, not whole thing. But we are measuring the multiple current at once. So some people put multi-label for the so we have concept for that whole thing parameters in that structure. That's something that measuring the monitoring when not different structure. So they have different both of these ones I told you, we have to model those kinds of lives. Probably it's definitely lifestyle, but that's different. When in different structure, we have to create a different model.
So related to that, is this still restricted to tailored test sites on the wafer, or are you measuring directly in product at this point? Well, so at least in the old days, you would, for this product, for this measurement, you'd have an intentionally built regular array that wasn't part of the functional test. It was just an isolated test area. And of course, the dream was all, Intels and the like don't like that. They want to measure directly on their product, but it's far less regular. So it makes the physical measurement much more complicated.
So are you measuring the test set, or are you measuring like the actual transistor?
Yeah, I think it's cool. Yeah. I told you that getting a reference is really tough, but once we play that camera screen, you just get the signal on and they do the inference using that. So we don't show anything. We can measure the size where we want. So if we want and now.
Right. And are you checking every transistor, or are you performing on some sort of sample?
I don't know what happened, but probably then not all of that. That's something that I don't have now.
Okay.
There's no more questions. Let's thank the speaker again.
Thank you.